Good day everyone. I am Clarice Joy and today I'm going to tackle about the designing complex system, and I have here the three topic outline. The first is introduction, second is complexity in infrastructure systems, and last is complex system addressing the design challenge. Introduction. Socio-technical systems are systems that exhibit both physical and social complexity. Network infrastructures, such as those for transport of people and goods and for provision of telecommunication, water, and energy services, are prime examples of socio-technical systems. Infrastructure systems are complex systems in view of their combined social, economic, and physical complexity. Nevertheless, many design engineers are involved in infrastructure development. Complexity in infrastructure systems. So, infrastructure system are socio-technical systems. The notion of infrastructure generally refers only the physical network that connect the suppliers and end user of an infrastructure-bound service. However, in our view, an infrastructure system includes, besides the transport and distribution network, the carrier, conversation, and storage facilities, as well as the governance, management, and control systems that are needed to make the system meet in functional expectation and its social objectives. The behavior of an infrastructure cannot be understood by merely studying the structure and behavior of it. Both are interconnected in many ways. The physical network and the social network are complex in themselves, and their interaction at the level of integrated social technical system present other domain of complexity. Next is and any infrastructure itself a highly complex network system that includes both a physical and a social network or actor network. Next is the complexity in the physical network. The physical network of infrastructure system consists of many nodes and links. Large-scale systems such as the European electricity infrastructure comprise a huge number of subsystem links and nodes, all of which are interdependent in several ways. If one subsystem is not functioning well, this may have far-reaching repercussions to the functioning of overall system. Moreover, the nodes of the network interact with and adapt themselves to their surroundings. Their reaction to external changes is often non-linear, which can result in unpredictable behavior of the system. As a whole, deterministic choice is one form of such unpredictable behavior. As the number of subsystems and interrelationships increases and as those interrelationships become more diverse, it becomes more difficult to gain an overall view of the system and to model it. Eventually, the system will become so complex that the analyst can no longer recognize or model it at all. The studies on complex systems often use the concept of agent for interacting elements in the system. In general, an agent is a model for any entity in reality that act according to a set of rules depending on input from the outside world. So, agent-based Modeling theory uses agents that act and interact according to the given set of rules to get a better insight into a system. For the emergent behavior, which is the behavior of the system seen as a whole, follows from the behavior of the agent at the lowest level. Next is complicity in the social network. In a multi-actor system such as the European electric power infrastructure, many actors are involved with different possible conflicting interests and hence different perceptions of reality. Again, agents may be used to model the system's elements, which in this case are people and organizations, in an analogy with the agents in the physical network. Each actor in the official network can be described as an agent that acts according to a set of rules determine that legislation and regulation, moral and cultural codes, and etc. In addition to those more explicit rules, each actor will have its own strategy. In the case of a driver on a motorway, behavior psychology may shed light on the determinants of individual driver behavior. If the actor is a firm of competing in the infrastructure, related market, business, economics, and strategy will influence the actor's behaviors. Actors, however, may also show reflection and learning. When faced with a similar institution for a second time, their behavior will be influenced by the lesson drawn from the first time. This specific characteristic of actors makes modeling them as a rule-abiding agents an extremely complicated, if not impossible, task. Next is the actors are interdependent. Each needs the cooperation of others. As in the case of the physical subsystem, the interdependencies can take various forms. As the number of the actors involved in a problem increases, conflicts of interest grow, and there is a greater variation in interdependencies. Eventually, it may become impossible for any one actor to understand the situation in its entirety, and the predictability of the action undertaken by any one actor is limited. Next is evaluation of the structure systems. Part of the problem with understanding behavior of structures is the most of the physical system were not designed as an integrated system but gradually evolved over time. A typical example is the way the electricity infrastructure evolved in the Netherlands. Like most infrastructures, it's originated is in local network, established through private initiative. City network were established around the beginning of the 20th century. Interconnection of local network and network expansion to rural, rural areas was forged through intervention of the public authorities. Over time, the density of inter and end user connection increased. Transport and processing function in the infrastructure were intensified to serve an increasing number of users and an increasing demand per users. During this evaluation, ownership and governance of the electricity infrastructure shifted from the private sector to the public sector. Until about a decade ago, most infrastructure were run as a public monopolized. The infrastructure value chain was fully integrated vertically. This was justified by the fact that the transport and distribution network have the character of the natural monopoly. Whether directly or indirectly, the government controlled the realization of the infrastructure and the universal provision of the public utility service by central planning and allocation of funds. Many infrastructure have gone through or are still in the midst of the transition from a vertically integrated monopoly structure to an unbundled value chain, with competitive markets being introduced in those segments of the chain that do not have a natural monopoly character. This transition does not directly impact the technical network, but mainly the social network. Characterizing the social techno system. From this analysis, this is evident that there are both similarities and differences between the physical system and the social system at the conceptual level. Um, the The main difference is that the components of the physical system are technical or physical artifacts, while those of the social system are reflective actors. Reflectivity means that the actors have the ability to learn, and this has three significant implications for complex system design. Uh, Actors display strategic and opportunistic behavior. They learn the strategies and interventions used by other actors and in time may develop means to the sidestep these strategies and intervention. This is known as the law of decreasing effectiveness. Every strategy is only temporarily effective because actors learn how to neutralize its effects. This enhances the dynamics of network. Actors are constantly developing new strategies to maximize their interest. Because actors are reflective and understanding of the process of interaction that will eventually lead of decision is crucial. So, in this process, the actor interact, learn, and display strategic behavior. The final outcome cannot be fully understood without knowledge of the process itself. This represents as a major difference compared to the physical system approach in the which the white box of a system functioning does not always have to be known in detail. Design challenge for complex infrastructure system. The overall demand for infrastructure services is increasing at the same time. Society, society, society demands an every higher reliability of service as we grow more dependent on infrastructure-bound services. As the performance of the infrastructure system is determined by the interplay of the physical and social networks, ensuring high service reliability has become much more challenging. Highly reliable services are more and more the outcome of network of organization, many with competing goals and interests. This creates new challenges for network design and for effective market and network regulation and new needs for communication. and information sharing. In, in the design of new infrastructure or in the design of expansion of existing infrastructures, the main challenge is how to deal with the many uncertain that the system will face during projected lifetime. Since infrastructures are deeply embedded in society, they are not only subject to rapid technological changes, but they also have to keep up with institutional and economic developments, such as deregulation, liberalization, or increasing oil prices. The challenge is to provide technical flexibility and budget flexibility to ensure the adaptivity of the initial design of these changes requirements. The market has a tendency towards capacity scarcity because no private investor is prepared to invest is unprofitable overcapacity for the public good. This poses new demands on infrastructure capacity management. Innovation are needed to make better use of available capacity. For the longer term, the tendency towards underinvestment in electricity generating capacity poses a serious threat to economic growth and social development. Research has shown that new mechanisms such as capacity market must be brought in place to alleviate this risk. Other concerns are emerging with respect of the network quality of the longer term. To the limited possibilities to directly intervene in the established layout of the physical system, an important option is to ensure that the collective action of players are straight towards the public interest through educate market design, educate network regulation, where the network has retained its monopoly character, and additional legislation and regulation for safety, health, environment, and etc. In view of private actors' interest, a better insight is needed into how individual investment decisions will be performed as a subsystem of the complex infrastructure system. Complex system addressing the design challenge. So designing complex physical systems, the system design of complex system differs from that of a simpler system in the majority of general design passive components. Functional requirements for a simple system design, this will be a straightforward description. The system must store data in a complex system design. The function will often compound possibly with different function for different actors. The system may also be distorted upon implementation. It will not be used in exactly the manner that the designers intended. The more complex the system and the greater the number of the actors in the implementation field, the more likely it is that distortion will occur. Objectives and constraints. Objectives and constraints. The degree of complexity is result is a massive number of objectives and concentrates that the client and other actors can impose on the design. If the designer wishes to incorporate all these requirements, the system is very likely to suffer from over specification, which precludes or any solution or realistic design. Moreover, the system designer will have to contend with conflicting objectives. The more complex the problem, the more difficult it will be to determine the solution space, let alone let alone select the best design from the various options. Design space. So even in the simple designs, the design space can quickly take on enormous proportions. For large complex system, the design space is particularly unbounded. Other actors may also attempt to incorporate systems into design space or to ensure that they are excluded. It falls to the designer to define the delineate the design space is the best as possible. Starting points. In complex system design, it is very difficult to find starting points for a design. The transportation of models and design option is not simple and will indeed often be impossible precisely because they are systems embedded in a multi-actor field in a specific institutional context. Modelings and model. The models map the design space into the functions, objectives, and concentrates. The system models that play a role in this part of the process can vary for some simple mathematical linear system models to complex probabilistic models or game theory models. The designer may also use agent-based models in order to model the complex additive system. Next is real option theory and exploratory modeling are examples of methods that are employed for modeling the infrastructure system given the enhanced design complexity described above. The former is a pricing approach as it treats future uncertainty as a business opportunity contrary to the other methods, which take a risk-aversive stance similar to financial option. It allows the designer to build a real option into the currently implemented design. The option may be executed or exploited if and only if it becomes viable to do so at a certain moment in the future. The already implemented real option would significantly reduce costs of redesign in the future, justify investment up front. Research so far has shown that improvement of 10 to 20% in the NPV can be achieved. For the case of designing and building infrastructures, this would imply that option could be built into a power plant, allowing it to operate on multiple fuels. The advantage in the example of using the real option approach is that the cost of implementing of a multiple fuel burner can be traded off financially against the associated cost of the probability that different fuels will have to be used in the future. In other words, the cost of flexibility can be made tangible in terms of monetary value. When the design and operation of infrastructures is required to be adaptive in view of deep uncertainties in decision-making process in the system also need be adapted. The operational stages of any system are already considered in the design stage. But also in this case of changing changing. Ownerships or distributed responsibilities, which is often the case in infrastructure systems that operation and maintenance must be executed as flexibly as possible. The design challenges for infrastructures should therefore also focus on maintenance and replacement strategies, as these are so intricately related to design. In fact, maintenance and replacement could be considered as heavily concentrated design problems. Innovation, construction, and maintenance, contracts, assets management, and risk management are just a few emerging strategies that deal with integrating the design and the operation maintenance challenges for infrastructure system. For complex social systems, the process of design should not be regarded as a process of modeling a desired reality. For a network of actors, a model of the desired reality would only be authoritative if it would be accepted by a critical mass of actors. Within the network, this is precisely the problem given all the differing interests likelihood of a model being accepted in extremely small. How can you consensus regarding a desired reality be achieved? Nonetheless, the characteristic of network of actors reveal that two familiar types of intervention will not be effective. Hierarchy or command and control will be impossible since no actor is superior to any other. An actor who nevertheless attempts to manage the process through command and control will only generate opposition. Management by expertise of management based on a content-based analysis is also unlikely to succeed. Knowledge and information will be consist statements based on a content-based analysis are always open to rebuttal. There is no such thing as unambiguous information in this situation. Attention, therefore, shifts to the process of decision making. A set of game rules of this type is termed a process design. Like the design of physical systems, in the engineering design tradition, process design is based on solid set of design principles. In interactive decision making process, actors must be sufficiently open with each other. The the core values of the actors should be protected during the process. The process contains incentives of process and speed. The risk inherent in a interaction or negotiation process is that in order to reach consensus, actual content-based expertise will not be fully taken into consideration. There can be no negotiated knowledge, only negotiated nonsense. The fourth design principle, therefore, is the result of interaction process must stand up to expert scrutiny. And that's all. Thank you.